Okay, so this is a kind of a plug and chug problem. We've got a vector field, we've got a surface, and we're going to go through our usual process. We're going to parameterize the surface, and then we're going to plug into the formula for the how to compute these vector surface integrals parametrically. So step one, parameterize the surface, unit sphere. I'm going to use what I will casually call the spherical graph parameterization, where rho is equal to 1, and then x, y, and z are, rho sine phi cosine theta, rho, again 1, sine phi sine theta, and rho cosine phi. And rho is 1, so that ends up being that. So this is a pretty convenient parameterization, by the way, of the unit sphere. It's a good thing to remember. We did an example of this somewhere back in chapter 2, I guess it was. So with that parameterization, let's write down our vector field. Well, let's see, wait a minute. We better find our in vector first. So xu, excuse me, not xu, x phi, let's call it. So we take the partials with respect to our two parameters. So x phi is, I didn't leave myself enough space there. Oh gosh, let's see here. So x phi, take the phi partials of all these things, cosine phi, cosine theta, cosine phi sine theta, and negative sine phi. Let's see here, x theta. So now theta partials of all this stuff, and we get sine phi, negative sine phi sine theta, sine phi cosine theta, and 0. And then our in. So cross product of these two things. Well, okay, let's see. This is going to be inconvenient, isn't it? Okay. Times that. I have negative sine squared. Oh no, the positive. Sine squared phi cosine theta. And then let's see. Sine squared phi sine theta. And let's see oh my gosh, okay, then we're going to have sine phi cosine phi sine phi cosine phi cosine squared, and then plus sine phi cosine phi sine squared. The sine squared and the cosine squared add up to 1, and I claim we just get sine phi cosine phi here. Does that make sense? Is everybody happy with this? Yeah.
I'm not positive about this, but can we do the second one again? I'm not sure.
This one here?
If there should be a negative.
Yeah. So it's this times that minus that times that, or it's the negative of that times that minus that times that. Yeah, it is. There's a lot of minus signs running around. Yeah, and I get this wrong. Not rarely. Okay. By the way, there's a calculation. So there's a problem somewhere in the book where we use I've forgotten exactly what section it's in, but where we use a parameterization very, very similar to this and go through and compute. It's probably in this section now that I think about it. But anyway, so going through here. Now to compute, let's see, this is a vector surface integral, so we don't have to compute a length of this at all. We just take this, and let's see, proceed. So we're computing vector surface integral, otherwise known as flux, through a surface of f. Now f is x, y, negative z. So x, y, negative z is negative cosine phi. So there's f in terms of our parameterization. Dot N, it's this guy here, sine squared. There's a lot of recopying in this stuff sometimes. Okay, and then d phi d theta, and now let's look at this integrand. Excuse me, this this integrand. Let's multiply this out. A lot of a lot of calculations here. So let's see here. Well, okay, so I've got I'm going to have sine cubed of phi cosine squared theta. And I'm going to have sine cubed phi sine squared theta. That's awesome. Because the sine squared and the cosine squared are going to add up to 1. Yeah. And then I have, let's see here, minus sine phi cosine theta. D phi d theta. So, all right, rewrite. This is just sine cubed phi. Then I have minus, let's see here, sine phi cosine theta d phi d theta. Okay, so maybe we can get lucky and something's going to go to 0 or something. Well, notice theta goes from 0 to 2 pi. And this term here, when you integrate theta from 0 to 2 pi, these are constants. And the integral of cosine theta from 0 to 2 pi is 0. Right, so I claim that this term is going to go away when you do your theta integral. Is that cool? Everybody happy with that? Okay. So what we're left with is just the sine cubed phi. And does the same thing happen with sine cubed? Well, not really. Phi only goes from 0 to pi. So it doesn't sort of go all the way around, so you can't make a symmetry argument there. So this one you have to actually just compute by brute force. And this is a Math 32 thing. There's a lot of little tricks when you're doing trig integrals, single variable trig integrals. The trick on this one is, let me just write down this more explicitly. So this is 0. Oh, I'm sorry, yeah. Right. Thank you. We're going to rewrite the integrand sine cubed phi as sine squared phi times sine phi. I'm going to put sine squared in here. I'm going to rewrite sine squared as 1 minus cosine squared phi. And now what you get is two terms. You have an integral of sine phi. That's easy. And then you have an integral of cosine squared phi sine phi, and you can do a u substitution with u equal to cosine phi. And then compute that one. So both, you get two terms this way, but they're both terms that you can deal with, while this one is not particularly easy to deal with directly. So let me just say ... There's a Math 32 calculations ensue. Like this?
No,
oh.
No, the other way.
This way?
Yes.
Yeah, like this.
You got cosine theta at the end.
Right here? Yeah, cosine theta.
On the above line above.
Up here, cosine theta.
This should be cosine phi.
Oh, gosh, I recopied that wrong. Okay, now where did I screw this up? Okay, so that, you're right. Okay. Okay, phi. That phi came from, that was our part of our normal vector n, and that n, where'd this come from? This was that times that minus that. Yeah, that's that thing where we had the sine square. Yeah, that's a phi. That's a phi. That should be a phi. Thank you. Okay, so, okay, well, too bad. I was hoping that this would... Okay, unlucky break then. Okay, well then, no problem. So this no longer disappears as an integral. But what you have is, well, this is even better actually. This is even better because let me rewrite it. Oops. Wait a second. Is it? No, I guess it's okay. Let's see. Is that still a minus sign? Yeah, minus.
Well, yeah, isn't
Yeah.
Isn't it just zero?
But see, it's all fees. So
But can't you pull out, like, can't you make it sine phi, cosine squared phi?
yeah,
Can you pull
absolutely.
out a sine phi out of that?
Then it's sine phi and then times cosine squared minus sine squared,
Or the other thing you could do, right? Is
or sine squared minus cosine squared. Sorry. Yeah.
you could consider the domain of phi as being from 0 to 2 pi, the domain of theta as being from 0 to pi, right?
No, that's not the same. Yeah, phi really does have to go from 0 to pi. I mean, it just doesn't. It doesn't work. On the sphere itself. If you think about, spherical coordinates, theta goes from 0 to 2 pi, and phi goes from 0 to pi. Yeah.
But I mean,
You can change the order that you write them down. You could put the phi integral on the outside, but that doesn't change the fact that phi still goes from 0 to pi.
But geometrically, if you said,
Yeah.
like, let's say you had a given x and y, and you said phi is...
Okay, I see it. I see where you're going now. The problem there is that you can only. You remember this formula that our stretching factor is. Oh, wait a second. Hang on a second. No, we're not using a stretching factor here. Hang on. Let me think about that. Later on. I'm a little scared of it. It might work.
I mean, the answer I got was 0, so...
And is the answer this other way 0?
Brute force, not using this
Yeah.
kind of...
So you worked it out this way and got 0.
Yeah.
Yeah. Well, that could be. I have to think about that. Okay, so.
Because, I mean, if you start here and you go all the way around, you have a
Yeah.
disk of
Yeah.
y equals 0, and then if you go x or theta 0 to pi, that disk then rotates and forms a full sphere without overlapping.
Yeah. No,
anywhere.
that's right. That's right. Yeah. No, that should work. Yeah, that's a clever idea. I mean, I'm always scared when I have theta and phi ranging anything other than these values. But since you're right, this is not. There's no stretching factor. The stretching factor is a length which involves an absolute value, which requires a constraint on phi. But there's no stretching factor here. We're not doing any constraints. It is just a cross product. The n vector is still just what it is, and yeah, that works. That should work just fine. Yeah. And then let's see here. And these functions are. Yeah, do you have, yeah, that's right. Okay, now let me think just a little bit more now. Sine cubed. So sine cubed is, you've got a symmetry argument. And sine theta, cosine squared theta. Yeah, no, that totally works. You do have to, I mean, one thing to be careful of is that, so what you're going to end up with then is an integral from 0 to 2 pi d phi, right, of, and let's look at, so you've got sine cubed phi, and then sine phi cosine squared phi. You have to persuade the reader that these functions here have odd symmetry over the symmetry line of this interval. In other words, that when you flip over phi equals pi, that these functions flip, and of course the reflection on the phi axis, if that's 0, that looks like a phi, doesn't it? If that's 0 and if that's 2 pi, the symmetry line is here at pi. So if that's phi, then here's the reflection of phi, and r of phi is equal to 2 pi minus phi. So you have to persuade yourself that when you plug this formula into these functions, that they really do go negative, and they do. Yeah, that's true, but it's not. I would say it's not quite sufficiently obvious that you know what I mean. Yeah, so you want to go ahead and write that down. And in fact, it might just end up being easier to do the problem this way because this integral is something you can attack by means very similar to what we did here, and not so bad. Yeah. Okay, but that's a great idea. I like that idea. Yeah.
How did you make it 0 to
I'm sorry?
How did you make the limits of phi?
On this one?
Yeah.
Well, so this was his clever idea of. So what he decided to do is instead of, if you think about the surface of the sphere, right, and how do you parameterize the surface of the whole sphere by letting phi and theta range? The more obvious way to do it is have theta go from 0 to 2 pi all the way around, and then phi just does 0 to pi. But he's pointing out, and this is a valid observation, that instead you could have theta just go from just 0 to pi for theta. Just go halfway around with theta, and then just with phi go all the way around. And you get these little sort of rotating circles that, sort of trace out the whole sphere that way. Now, that only works because we're doing a vector line integral here, and we're not computing any lengths. That length calculation involves square roots, and you get absolute values and stuff like that, and it gets weird on this. But for this as a vector line integral, it works okay. I'm not persuaded that it's actually easier this way. I still kind of think that the easiest way to do it is to just parameterize in the normal way and note that these integrals are just simply not that bad and just write them down. Yeah, I'm sticking with this as being still the best way to do it. Yeah. Okay. All right.